Yes, I guess we can start. Yeah, so let's wait for 2 3 minutes more and then we'll start. Yeah, so I guess we can start. Let me share the screen. Yeah, so good evening all. Welcome to week 11 problem solving discussion session for this NPTEL PMRF teaching assistance course. So this is NOC 26C32 uh, interactive sessions, which is for the geotechnical engineering to foundation engineering. Myself, Ritura Singh Srawat. I am currently working as a Prime Minister Research Fellow in Department of Earthquake Engineering from IIT Roorkee. And this course is currently being tutored by Professor Dilip Kumar Bedia, who is a professor in Department of Civil Engineering from IIT Kharagpur. So those who are joining this session for the first time, let me tell you, these are the interactive sessions which are meant to interact with our learners. We'll be discussing some of the important concepts which will be required to solve your assignment problems. Along with that, we'll be solving some of the sample questions which will be helpful for you to solve the assignment question. We'll be solving some of the doubts related to that particular week's lecture. Apart from that, if you are having any other query related to the career guidance or let's say related to the research, we'll try to help you till whatever extent it's possible. So let's start our session today. So I'm audible, right? You can ping in the chat box.
Yes, sir.
Sudhanshu, am I audible?
Yes, sir. Uh,
Hello. Okay, okay. Thank you, Sudhanshu. So let's start our first question of the day. So first question it's like this. So when we design the brace cuts, the earth pressure distribution is based on. So on what theory the earth pressure distribution is based on?
C option, sir.
So it's the apparent pressure diagram. One second, guys. Yeah, it's working. Yeah, now it's right. Thank you for this. So let's check the solution. Yeah, so the correct answer is apparent pressure diagram. Let me check with the answer which I'm having with me. Yeah, so the design of the brace earth cuts is basically based on the apparent pressure diagram. Moving to question number 2, you have been given with a trench of 3 meter wide, 7.5 meter long, and it's excavated in a medium dense sand. The side of the trench are supported with sheet pile walls fixed in a place by strut and well, that is braced excavation. Assuming gamma is equals to 18 kilometer per meter cube and phi is equals to 30 degree. What is the maximum pressure against the sheet pile sheet pile wall? Yeah, so let's check the answer for this. So apparent earth pressure is basically given by this like this. So you are having a wall and the pressure is something like this. And the maximum pressure is given by 0.65 H gamma Ka, which is this is your height of the wall. Ka is your none other than 1 minus sine phi upon 1 plus sine phi. So this is based on the apparent pressure diagram, and the maximum pressure, as we know, is your 0.65 H gamma Ka, which is your 0.65. H is your 7.5 meter, and gamma, which is given to you, is 18. K is your 1 minus 1 by 2 upon 1 plus 1 by 2, which is your none other than 1 by 3. So it's 1 by 3. So 6. So let's calculate this. How much is this? It's 29.25 kPa. So yes. So any doubt in this, Sudhanshu?
Oh, no, sir.
Okay, then let's move to question number.
I think my microphone is not working properly.
Let's move to
I'm
question number.
audible, sir? I think
Ye-
microphone is not
Yes,
working, I think.
Sudhanshu, you are audible. No, your microphone was working. Actually, it was mistake from my end. My volume was low, so I couldn't able to hear you.
Okay, sir.
Okay, Sudhanshu. Let's move to question number 3. So you are having a cut which is a 3 meter wide, 5.5 meter deep. It's proposed in a cohesionless soil which is phi equals to 36 degrees, C equals to 0, gamma is equals to 18 kilonewton per meter cube. Assuming the first row of studs to be located 0.5 meter below ground surface and spacing between the studs as 1.5 meter, what is the maximum stud load with the horizontal spacing of studs as 3 meter? Okay, let's check this. So you're getting D, 75.15. So how did you solve this?
Sir, basically, I first find out maximum pressure
Mm-hmm.
by last problem, just like last problem. It's coming 16.65. After that, I take horizontal spacing and tributary height, like converting zero point 0.5 and zero point 0.5, cancellation and 1.5 spacing in between, like
Okay, so
from
what are the spacing? 0.5 meter and
1,
1.5 meter.
1.5 meter in between major steps, and uh, for from ground level and from last most portion, I lose the zero point 0.5. Yeah. Yes.
Okay,
In between, I take 1.5.
and in between it's 1.5, right?
1.5. I take that, sir.
So in this same formula you might have taken, so 0.65, H is your
In
1.5, right?
yes,
And
zero
gamma
point
18, and K
18,
value, how much is K?
0.259.
So it's basically 1 minus sine 36 upon 1 plus sine 36, right?
Yes, sir.
Yeah. So PA is your this one. So how much you are getting this?
I'm getting, sir, is 16.65.
16.65. Okay. So 16.65. So this is a PA which you are getting.
Yes, sir. After that, I multiply with spacing in horizontal and
Mm-hmm.
1.5.
Okay. And so horizontal, how much is the spacing?
3
It's 3 meter,
meters.
right?
Yeah.
Yeah. So PA, maximum PA is your none other than 16.65 into 3. Were you getting this 16.65?
Uh, yes, sir.
So how much answer you're getting?
Sir, 0.6. No, sir. PA is 16.65. After
Okay.
maximum PA is 16.65 into 3 into 1.5.
Okay. Why 1.5?
Sir, spacing in between verticals.
Yeah.
2 and
So
3, there is a
basically you need to
maximum.
calculate the pressure. So both the vertical and the horizontal you need to take into account. So 3 was your horizontal spacing and 1.5 is your vertical spacing, right? So how much is the answer?
Sir, it's 75.15 closer.
75.15. Yeah. So correct answer is this. So this is top side view. This is the top view, which is your 1.5. This is your 3 meter. So correct answer is 75.15 kPa, right?
Sir, I have doubt. Can you please explain me the
Okay, it's
phenomenon of
kilonewton. Sorry. Yeah.
maximum?
They are asking the load. So maximum load. Sorry. Yes, please.
Sir, can you please tell me the phenomenon of maximum P, like of
PA.
why we take 3 and 1.5? Like I directly take
Maximum
the
P.
formula.
Okay.
Yes.
So like as you can see, first we will consider calculate the pressure. So this pressure basically, if you are seeing the from the elevation point of view, right? So from the bottom it's zero point 0.5, and from the in between the studs it's 1.5 meter. Okay, so definitely like in between these two struts you can assume that there will be the maximum pressure which will be going to act, because there is a maximum spacing between these two, 1.5 meter. And at the same time in the horizontal also, so this is your elevation view, and if I see from the side, okay, and if I see from the top portion, so these struts, so from the top it will look something like this. So 1.5 meter, and here you will be having the 3 meter. So from the side if you will see, it will something look like this, 1.5 meter and 3 meter, and here is your whole pressure acting. Because here is your one strut, here is your one strut, here is your one strut, and here is your one strut. So now this pressure we have evaluated, how much is this? This is 16.65 kPa. Now if you want to convert this uniformly distributed load or uniformly distributed load into a single point, into a concentrated load, so you need to multiply this pressure into this uh, area
area.
of this diagram. So this is 1.5 into 3, so which will basically give you the 75.15 kilonewton.
Okay. Okay, sir.
Okay, so are you clear with this?
Yes, sir.
Okay, so let's move to question number 4.
Yes, sir.
1 second. So this is your 75.15 kilonewton. Let's move to question number 4. So now we have come to the soil dynamics part. So with K and M as the spring constant and mass of the system respectively, and C is the damping coefficient, what is the system? The system is under damp under which condition? Like among all these three conditions, in which case you will consider the under system is under damp?
Sir, I think slide is not.
Yes, sorry, 1 second. Yes.
Sir, option C.
Option C.
Yes, sir. It is
Okay, so
underdone.
what is the condition for under dam?
Sir, third, because it should be less than root k upon m.
Yeah.
It's critical than second condition, I think.
So C by 2m. What is C by 2m?
Sir, C by 2m is uh, coefficient. It's ring coefficient and mass k and m.
Yeah, no worries. So this is, yeah. So yeah, the correct answer is option C, which is C by 2m is less than root over k by m. So usually it happens in the case uh, when your C is less than C critical. And how do you define the C critical? So omega n square. So xi is basically given by 2n omega n square. 2m omega n. Yeah. So C is equals to xi square. 1 second. I need to check this. So critical damping ratio. So when C is less than C critical, C critical, C critical is given by, yeah, 2m omega n. 1 second, yeah. Let me check this. Actually, yeah, I was right. So C critical is your none other than it's your 2m omega n. So whenever your uh, damping coefficient is less than the critical damping coefficient, which is your C critical. So which is given by 2m omega. So in this case, it is considered as the under damped system. So let me define this. How do we say this case? So let's say if you are having uh, consider a case of a door. So let me draw a top, not a door. Yeah. So let me consider a case of a spring mass system, and this is your M. So let's say if you push the mass against the spring, if you push the mass against the spring, if it comes to its original position, then we can say it's a critically damped system. It's a purely elastic system and there's no damping available. So let's say if I'll push the mass against the spring, let's say it got displaced by H and it rebound to its original position and by H and it comes to its original position M. So there is no resistance which has been offered by this surface, and in this case your system is basically elastic system and there is no damping available. But in the realistic or in the true nature, it is uh, never possible such that your system is purely elastic. There will always be some damping which will be available, and for that you will be having three type of damping, three cases: the critical damp case, uh, the under damp case, and the over damp case. So let me give you the example of the critically under damp and the over damp case. So consider a door uh, and which is having a door stopper. So when you close the door, then it doesn't come suddenly back to its original position. It comes very slowly. So that type of system we call it as a under dam system. And critically damped system, when the coefficient of that frictional resistance which has been offered is equal to the 2m omega n. So in that case, C is equals to C critical. So and over damp system, it's very difficult to find, but there's one viscous damper which you can say, which is a over damper system. So these are some of the examples. I'm not able to recall the critical damp system, but once I'll get this, I'll let you know. So critically damped system, I think I'm having in that solution. As you can refer the textbooks, that will basically help you. I'll try to come up with the examples in the next class. So I'm not able to recall that now, but yeah, I'll help you in the next class. Sure. Let's move to question number fifth. So as per IS 2794, the permissible amplitude of the reciprocating machine is. So you need to find what is the permissible amplitude which you can allow for the reciprocating machine.
Option B, sir.
Yeah, how much you're getting? 0.2 mm. Yeah.
Point 2 mm.
So the correct answer is 0.2 mm. So whenever, let's say on any floor or any ground surface of the building, if you place a certain machine and if you make it vibrate, let's say in the vertical direction, so the allowable displacement amplitude of this floor which you can allow is not more than 0.2 mm. So the correct answer is 0.2 mm. Moving to question number 6. If omega is the operating frequency and omega n is your natural frequency, which one of the following condition is correct for the design of a dynamically loaded foundation? So how much uh, natural frequency, in which design criteria, design frequency you should keep your operating frequency?
Sir, can you please explain this answer?
Yeah, so it's basically, the correct answer is option A, which is zero point 0.5 omega is greater than 1.5 omega. So this is the case. So whenever, so let's say you are having a certain foundation. Okay, let's talk about the uh, shallow footing. So whenever it's getting vibrated, let's say in the vertical direction, whenever it's subjected to, let's say, some dynamic load, so it will vibrate with certain frequency. So first, this system will be having their own frequency, which it can, the intrinsic property of this footing, the dynamic property. So that basically correspond to the, you will call those that frequency as the omega n. And then when you apply a dynamic load to this footing, then due to the action of this external load, this footing, let's say, will vibrate with frequency of omega. So now, which one of the following condition is correct for the design of a dynamically loaded foundation? So usually in this case, your natural frequency means you need to design your foundation in such a case such that your omega n should not be near to your omega, because you might have heard of the condition of the resonance. So resonance is the case when your natural frequency is equal to the loading or excitation frequency. So in this case, this is not equal to, and usually we keep a certain margin. So in this case, your we design our foundation in such a case, such that your omega n is less than zero point 0.5 omega and it's greater than equal to 1.5 omega. So when I say designing the natural frequency, so omega n we know it's given by 2 pi root over k by m, right? So you know k and m. So stiffness is basically the function of your geometry and your material, right? E. And your mass is, it's inherent, it's a property of the system. So this is your mass. So this is your inertial uh, property. So this g is basically so f is function of your geometry, and your geometry is also denoted by I. So you need to design your footing in such a case, considering the geometry, material, and mass, such that the natural frequency which you get, it should not be in the range of it should always be in the range of this zero point 0.5 omega and 1.5 omega. So that's I want to like basically show you. Do you want me to repeat this again?
No, sir, I understand.
Okay. So it's basically to avoid the uh, phenomena of the resonance, basically.
Okay, sir.
So
Sir, which reference book we should take?
for the this thing, uh,
Yes.
here basically there's one book known as the Dynamics of Structure, given by which is written by A.K. Chopra. So you can refer that.
Sir, dynamics of
Structures.
structures. Okay.
Yes, yes.
AKCHO.
A.K. Chopra.
Okay, sir.
And there's one more book which is known as Geotechnical Earthquake Engineering
Geo.
by Kramer.
Mike Arima.
So if you want to go only understand the geotechnical part of the dynamics, so you can refer that geotechnical earthquake engineering. If you want to understand the uh, dynamics in office structures in a more detailed manner, then you can refer the AK Chopra book.
Okay, sir.
Okay, then let's move to question number 7th. Then you are having an unknown mass which is attached to an end of an unknown spring K, and the natural frequency of the system was found to be 85 cpm. If 1 kg mass is added to m, the natural frequency reduced to 70 cpm. The value of the unknown mass is. हाँ बताओ, प्लीज सुधांशु.
uh, sir, little bit difficult. I'm getting in answers.
uh, shall I solve this?
Oh, yeah, yes, sir.
Okay,
Sorry,
Sudanshu.
I
Okay,
take
no
more
worries.
time.
So basically the natural frequency which is given here, it's basically reduced to 70 cpm. The natural frequency reduced to 70 cpm, right? So it is the case when 1 kg. Okay, so initially it is 85 cpm and the spring coefficient is k. So the system is somehow given like this. So you are having a spring and this is your mass m, and your spring is k, and the natural frequency of the system is found to be 85 cpm. Now here it is given. So this is for the case when your this is your k comma m. Now they are saying if m dash, if new mass is equals to m plus 1, then your natural frequency, the omega n, basically reduced by 70 cpm. So this is for the case for uh, k comma m plus 1. So now if I'll solve this, so omega n we know is given by root over 2 pi k by m. Omega n is equals to 2 pi f is equals to k by m. So k by m, and your omega n is given as 85 cpm. So 85 cpm is basically 85 by 60. So cpm is basically cycles per minute, and cps is equals to cycles per second. So 85 by 60, 85 by 60 is CPM, cycle per second. So it's 1.41 CPS. 2 pi root over k. K. Okay, so you don't know how much is the k value. So k value you need to basically evaluate. So omega n 70 CPM, 85 CPM, k. So k is basically the natural frequency of the system reduced to 70 CPM. So let me check whether they are talking about the natural angular frequency or natural frequency. Yeah, so they are basically talking about frequency. Okay, so this is not the angular frequency, this is the frequency. So f and the f dash. So your f is basically f is given by, okay, let me take a new slide. Yeah, so we are basically first talking about the frequency. So frequency is given as 85 CPM. So when you convert into the cycles per second, so it's a 60. So yeah, it's 1.42 cycle per second. And when you convert the 70 CPM into cycles per second, so 70 by 60. So how much is 70 by 60? It's 1.17 cycles per second. Yeah. So in the first case, basically they are saying the natural frequency is this, and then this is this. So your f1 is basically 1.42 CPS, and f2 is basically your 1.17 CPS. In this case, your mass was m, and in this case, your mass is basically m plus 1. So the value of the unknown mass you need to basically determine. So we know f is equals to root over k by m, right? So for the f1, it's basically k over, because there is no change in the stiffness. So this is basically m, and f2 is basically your k upon m plus 1. So this is 1, this is 2. So if I divide 1 by 2, so this is your f1 by f2, m plus 1 by m. So the whole root is given f1 by f2 m plus 1 by m. So f1 is your 1.4217.
Sir, how we convert that root k upon m and root k upon m plus 1 in inverse?
So I have divided 1 by 2. So f is basically uh, omega n is your 2 pi f n, right? And omega n is also 2 pi root over k by m. So your fn is basically your k root over k by m. So f1 we know in the first case you have been given there is a mass m and then there's an unknown spring k. Then in this case your natural frequency was 85 cpm, which if we convert into a cycle per second divided by 60, so 1.42, and here it is divided by 60, so 1.17 cycle per second, right? So 1.42 divided by 1.17, and in the first case mass is m, and in the second case you have been given the 1 kg mass is added to m. So in the second case your mass is m plus 1. So this is your m kg. Sorry,
Uh,
is the slide
so,
visible?
yes, sir. But what we have to do with root k? We have to cancel it.
Yeah, we have to cancel it, yes.
Okay.
So
So that's why we take inversely because it's 1 upon m.
yes, 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 yes.
Okay.
So with this, can you calculate what is the value of m?
Yes, sir. 1 minute.
Yeah.
1.4. Uh, Sir, the 1.473 m plus 1 upon m. M slides here. So 1.41 m is equal to 1 plus m. M get cancelled. So 1 by 1.47. 1 by it's 0.67. 1. Uh, it's getting, sir, 0.67 m. M is equal to 0.67. 7, I think do some mistake.
How much you're getting m?
Uh, Sir, M is getting 0.67. I think
How much we are having? Answer. Okay, let me
think
check.
it's coming in 0 point something.
The answer which is there with me is little different. Okay, you can also but No, it's not possible.
Um,
How much you are getting?
Sir, 2.11. Now I think I recalculated from calculator.
Okay,
Scientific.
M is
2.11.
2.11. Yeah, I am having the answer as C, 2.14 kg. Yeah, so it's fine. So the correct answer is C. M is equals to 2.14 kg.
Okay, sir. Oh, sorry.
So let's move to question number 8. So now they are basically asking to calculate the spring constant K of the system. So we already know what is M. So we know F1 is equals to root over K by M, right? F1 is how
Two,
much?
two by, sir, 2 by
1.4.
root.
Sorry?
Sir, root. You have to take directly K formula.
Yes, yes.
Uh,
Directly you can take. And M is your
because
2.114. Now calculate how much is the K.
1, 4 square 2.01. 4.34. No, no. K is not 4.3.
K is how much?
Uh, 1 minute, sir.
Yeah, no worries.
4.31. I'm getting answer, sir. This K is 4.31. Sir, I'm getting is 4.31.
4.31.
Yes, sir. By calculating equation 4.42 is equal to root K upon 2.14.
Okay. kg meter. So spring constant. Okay, we need to evaluate in the kg per meter. So cycles per second, 1 kg mass. So you are getting answer 1.42 square. So it's cycles per second. So here it will come out as kg per meter. Yeah. So K mass. So
Sir, I think screen is not visible.
yeah, frequency is
Make
your.
visible.
Sorry.
Yes. Sir, screen is not, I think, updated.
Okay, screen is not visible.
Yes, sir. It stopped, I think.
1 second. I'll share that again. Frequency, it's okay. 1.42 K. So K is basically is your 1.42 square into 2.14. So the spring constant K of the system. So how much you're getting this?
4.31.
4.31.
Yes, sir.
Mhm. For this, were you getting m is equals to 2.14? I'm getting it as 1 second. Frequency, it's given me in terms of the 1.42 cycles per second. Okay, sorry, I'm so sorry. I have confused you with the formula here. So omega n is your 2 pi f, and f is basically your root over k by m. So omega is basically your k by m. I'm so sorry. So when it comes to f, so it's your none other than f is equals to 1 upon 2 pi root over k by m. Sorry, 1 upon 2 pi root over k by m. Yes. So this is your k by m, k by m. So in this case, when you solve this, so okay, here it's turning out correct. So, okay, so there is not, it's basically 1 upon 2 pi, 1 upon 2 pi, 1 upon 2 pi. So, fortunately, in this here it was getting cancelled out, so 2 pi got cancelled. But here f1, if we'll calculate, it's basically 1 upon 2 pi. So now if I'll calculate this, so k is equals to 1.42 into 2 pi whole square into 2.14. So if I'll check this answer, 1.42 into 2 into 3.14 into 8.91 into 2.14. Yeah. So now it's coming out as a closer to 169.7 kg per meter. So which is your option A, 169.51. So there was one small mistake I have done here. So omega n is your k by n, root over k by n. Okay, so the mistake was from very previous, anywhere else. Yeah, so just take the note of this omega, so we won't get confused in the future. Omega n is your root over k by n. Time period is your 2 pi by omega. So time period is your 2 pi root over m by k. Frequency is 1 by time period. So it's basically 1 upon 2 pi root over k by m. Sorry guys, sorry. It's been a while I have touched this. So just always remember this. So omega n is equals to root over k by m, time period is equals to 2 pi by omega, and frequency is equals to 1 by t. So which is your 1 by 2 pi root over k by m. Sudhanshu, is it clear?
Yes, sir. Yes.
Yeah. So let's move to next question. So the rotation of a block about z axis is known as. So let's say when you are having a certain block, and this is your z axis, this is your y axis, this is your x axis. So when I'm rotating this box around this axis, so what do we call that type of vibration?
Horizontal. So, yeah. I think. Is it, sir, horizontal vibration? I think. No. Horizontal. Vertically also not there.
So what type of vibration it is?
Uh, Torsional, sir. I think torsional or horizontal. I have bit
It's
confusing
torsional,
because it.
definitely. So let's say if this is your building, so if it's vibrating in along the x-axis like this, so this is your horizontal vibration, and if it's vibrating in this axis, so this is your vertical, and if it is rotating about this axis, so this is your torsional.
Yes.
So this is your torsional vibration. Correct answer is option A. So the rotation of a block about z axis is known as the torsional vibration. So let's move to question number 10. So the ratio of the damping coefficient in a given case to the critical damping coefficient is given is called.
Damping factor, sir.
Uh, so the ratio of the critical of damping coefficient in a given case to the critical damping coefficient. So let's say C to C critical. So that is basically your critical damping ratio. So the correct answer is C. Yeah, it's the damping factor. So which is denoted by xi. So xi is your C by C critical. So it is denoted by damping factor. Let's check. It's, yeah, it's basically known as the damping ratio. But here is the critical damping ratio. Yeah, so I think the damping factor or damping ratio. Yeah, it's not critical damping ratio, but it's also known as the damping ratio. So the widely used term is the damping ratio. So xi is equals to C by C critical. So we can also call it the damping factor because it is not the critical damping ratio. So damping factor is right. To question number 11th. Which are the parameters required in the analysis using the mass spring dashboard model?
Sir, C option, both A and B.
Yeah. Let's move to question number 12. The maximum displacement of a vibrating system from its equilibrium position is called its.
Amplitude.
Amplitude. Okay.
Amplitude.
Let's check the answer. Yes, it's amplitude. A machine foundation which is weight 85 kilonewton and mass, okay, weight is given to you 85 kilonewton of machine foundation. K is your 11,000 kilonewton per meter. The system will be critically damped if the damping coefficient Cc. So you need to determine what is the Cc in case of the critically damped. Did you get any answer?
Uh, uh, No, sir. 1 minute, sir.
Yeah, so we know for the critical damp case, your uh, coefficient is basically equal to the C critical. So the system will be at the dipping coefficient Cc. So in this case, your Cc is basically given by, we know it's 2m omega n and 2m root over k by m. So Cc is your none other than 2 root over km. So can you solve this? What you are getting? 2 km. So 2 11,000. And then this is your mass 85 kilonewton. When you'll convert into the Newton,
Sir,
1000,
we have to take 9.81.
then into the, so this is your basically conversion to Newton, and then this is conversion into kg.
Sir, but
Okay, so
the
it's 9.81.
9 point. 191.54. It's getting, sir.
How much you're getting? 191.
191.54 into 10 raised to 3.
uh, did you take the root of this?
Yes, sir.
So Cc is
11,000.
equals to 2m omega n. M is your, okay, it has been asked in the kilonewton second meter only, so you don't need to convert it basically. So 2 root k,
11,000.
you can directly take in the kilonewton, and then k is 11,000, and then your mass, okay, it has been
85.
mass is also 85 kilonewton.
Sir, what is value of m? Sir, we have to take first, I think,
Sorry.
2m. So 2m value of m we have to take, sir.
I'm basically, you need to take the 85 kilonewton only, so you need to convert from that.
No, sir. In formula of CC, 2m root k upon m. So we don't we don't take that m value to m.
Yeah, so basically this m basically will go, this is root m and m, so this will go into root m.
Okay.
So 85 kilonewton. So kilonewton, so converting into the mass, so that will basically, okay, it will get divide by 9.81. Yeah, now it makes sense. So mass, so weight is your mg, and m is equals to your weight by g, right?
Sir, I'm getting is 617.44. Option
Six
C.
617.44, right?
Oh, yes, sir.
kg, ठीक है, okay.
Option C.
C, right? Option C, 617. Then let's move to question number 14. So if mass equals to 3 kg is attached to the end of an unknown spring K, and the natural frequency of the system was found to be 90 cpm, what is the value of the unknown spring constant K? So the system is basically given like this. So you are having a spring of coefficient k, then this is 3 kg, and this is m. K is basically, you need to determine, mass is 3 kg and the natural frequency of the system is 90 cpm. So it's 90 by 60, so which is your 1.5 hertz. So you better know this, that frequency is equals to 1 upon 2 pi root over k by m. So 1 upon 2 pi into root over k, mass is your 3, fm it's 1.5. So k you need to determine how much is k. So k is your 2 pi into 1.5 into root 3 whole square. How much is this? So can you calculate this?
Yes, sir. Sir, 266.47 option.
266.47, right? So
Yeah.
option B, right? Yeah. So the correct answer is option B. So did you get this?
Yes, sir.
Yeah. So most of the questions in this, like it mostly based on the damping ratio, critical damping coefficient, and then you are having this the relation between the frequency time period and the natural frequency, angular frequency. So just try to get along with that. So I think we can close for today. Do you have any specific doubt you want to discuss upon?
Uh, no, sir. Right now. Sir, can you please again see me the reference books? Yeah.
Yeah, you can refer the dynamics of a structure, which is A.K. Chopra.
A.K. Chopra.
Yes.
And geotechnical engineering and
Geotechnical
aeronautical
earthquake engineering.
engineering by
Kramer.
grammar.
Kramer. Kramer.
Okay, sir. Sir, for geotechnical, the which reference book I can like I have follow this KR or no? Is that okay, sir?
Yeah, so KR Arora is fine for the, you are at undergraduate level, right? Right now?
Yes, sir. Yes.
Yeah, it's fine. So you can go. Otherwise, there's one more book by the Gopal Ranjan. You can refer that. So yeah, it's fine for the UG level. You can refer those books.
Okay, sir.
Yes,
Yes.
yes.
Thank you, sir.
No worries. Thank you, Sudhanshu, for joining. So, uh, so thank you so much, guys, for joining. Those who are watching these videos at the latest stage, you can post your queries in the comment section of the YouTube video. I'll definitely address your query over there. So thank you so much. We'll meet again on next Tuesday at same time. Thank you so much. Oh, sorry, not on the next Tuesday. I think we are having one more session class tomorrow. Let me check. I think I got the mail also. Yeah, there's one class scheduled tomorrow, which is at 5:30 p.m. So actually, we need to take one more extra session as instructed. So, uh, like. You guys can join tomorrow also. There will be one doubt solving session tomorrow also at 5:30 p.m. So please try to be available at that time.
Okay, sir.
Okay, okay, guys. Thank you so much.
भाई वो आ जाएगी ना मुझे, तो मुझे चाहिए नहीं लाइफ।